Okay, hello, this is Stefan Koch, and let's hope that this time we will actually be able to record the video and not like the two times before where either the sound was missing or the video wasn't saved. Now, at least I now have experience in making this tutorial, and first let me tell you what we will be doing. I am hoping to show you how the bytecode works. I invented for newCTFE, and because it's a generic bytecode, you can do anything with it you want, and it works at CTFE, so it's really nice to use. And will eventually be accelerated by jitting or something. Alright, now first let's make a file that uses the bytecode interface thing, interpreter, and for this we need to import the bytecode, which is called ddmd.ctfe.pc is the bytecode interpreter, and we have also the common definitions for this stuff. And we can just start with normal main function. And probably we should import the standard IO as well in order to read and write stuff to the output. Okay, now let me actually make a codegen, and then I use my favorite this clause, so I can call the member function without having to write gen in front of it, and then it looks like a pretty nice domain-specific language. So the first thing you need to know is that every generator needs to implement finalize and initialize methods, and those have to be called as initialization step and before you interpret the code. So the first thing you do is calling initialize, right? And finalize comes after that, right? Between those two calls, you can now issue your calls to generate a function. The first thing you need to generate a function is to generate the function signature. So the return type is implicit because it doesn't matter, but the type of the parameters, they do matter, because we have to deal differently with pointers than we deal with integers. Actually, that isn't really the case, but in order to document what stuff is, it's still very useful to know what those parameters are. That's why you have to give them a type. And we want to have a parameter, and if we want to make a parameter, we said auto p1 equals gen parameter and the type, and the type has to be of type bc type, and we want the bc type of bc type enum of i32, and this corresponds to an int. Indeed, this is a signed 32-bit integer, and because you use them so very often, this type is actually defined in the common file. I can quickly show you how it looks like. Yeah. Just static immutable, and then BC type enum I32. That's all this is. So we could write this one as well, but I32 type is just simpler. Alright, no. And maybe we should first have a function we want to write. So let's write pow. What does pow need? Pow needs the base, right? Whoops, I just wanted to move this one, right? It needs the base, and it needs the power we want to raise to. So generate a second parameter that's also of I32 type. And then we can begin the function body. We do this with begin function. And we have to give a function number. And function number 0 is done implicitly. And function number 0 will always be the function that will be interpreted when we call the interpret call. A begin function has a corresponding end function, and in here we can write the function body. So what do we need for pow? Well, we could do this. We could say while this is the decode we would write. While pow minus minus say base times equals base, right? But this wouldn't be right at all. So we need we need to make a result variable. So it would look like this: and result equals 1 while pow minus minus result times equals base. Then we return the result at the end. And this will work. So if the power is 0, we will never execute this, and the result we will return will be 1. So anything raised to the first power is 0. If the power is 1, we will return this once, and this will be 1 times equals base, so 1 times base, so the first power is the base itself, and the second power would do 1 times equals base, this then equals base, and then times equals base, and then we have for 2 it would expand to base times base, which is also correct. So this is, I hope everybody can see that this is the correct code to raise something to an integer power. So let's do this before the function. So this is what the body should represent. Now, in lower level code, we do not have something like a while. We have to do this with jumps and conditional jumps and labels. Everything is jumps, labels, conditional jumps, and math. That's all your computer does. Your computer is just a big calculator with access to memory and the ability to check if something is 0 or not. Right? That's all you can do. and some floating point stuff and some special hardware interaction. But basically you just have a big dumb calculator which has memory attached to it. That's all your processor is. So that's all we do in our bytecode. Alright, first we need to do this. Int result equals 1. And we just say result is just a temporary, because we don't need it after the function has ended. And yeah, it's of type i32. That's all this is. This is equivalent to this. Now the while power minus gets a little more tricky. So we are going to rewrite this into this. If we don't have the power, so if the power is 0, if the condition power evaluates to false, we want to return result. Okay? And if this is not the case, we want to go to else we want to do this. We want to do the label else we want to do result times equals base and then power minus equals 1, right? And then go to begin loop, and this would then be here, begin loop. Okay, I hope you can see that this would do the correct thing. So this is what our what this becomes, right? And this is something we can actually do. So we say we have to generate the label, begin loop, and then we generate, we begin a conditional jump, and what do we write into that begin conditional jump? Well, let's look at the function signature of begin conditional jump. So begin conditional jump has a BC value and a boolean that says jump if true, right? I want to jump to the label we specify later if the thing is true, right? And normally it jumps if this condition evaluates to false, or if it is 0. But when we set this to true, then it will jump if the condition is true. So, and what do we want, right? So if this condition here is false, we do the return. So we go on, which means that we want to jump if it is true. So what is the condition? The condition is if the power equals 0. Begin conditional jump power will normally jump if the condition is false. So this is if not pow jump to label and label, right? And otherwise it will go on. There's no clause that's just if that condition is false, jump, right? But we want to jump if the condition is true. When we want to jump if the condition is true, look again, then we need to set the if true to true, which is normally false. Alright? So if we don't jump, here is where we will get, if we don't take the jump, we will be directly after this. And we want to return the result. The instruction for this is ret, right? And we want to return the result. Okay? Now, good. So we need to make a label here because this is where we want to jump. Oh, not gen label. Gen label is the function. This is the mul loop label. Gen label. And this is where we want to jump if this is false. So we say and conditional jump. Oh yeah, and we have to save the jump itself. To be able to end it, we need to save it. So we want to end this conditional jump. And it should go to the label we just generated, mul loop label. Okay. So if this condition evaluates to false, we will end up here. If it evaluates to true, we jump to wherever this label is. This label is here, so we jump to here. So we will end up here. Where we are right now, we will end up if the condition is false. No, we jump if true, so we will end up here if the condition is true. And what do we want to do then? Well, what we want to do is first we want to subtract 1 from the power. Yeah, and probably I should show you the function signature of sub 3. The function signature of sub3 goes like this. This void bc value result, bc value LHS, and bc value RHS, and it will do result equals LHS minus RHS. And when we plug in pow 1, we get out pow 1, right? And this then equals pow minus equals 1, right? This is what we do here. We do pow minus equals 1. And then we need to do the multiplication. And the multiplication is written exactly after the same pattern. So first comes the result. We want the result to be the result. Then we want the LHS to be the result as well. And we want the RHS to be the base. So this will be result times equals base. Okay? Okay, now when we are done with this, we need to evaluate our condition again. And for this we have to, this has to be auto. For this we have to be jump to the begin loop, and there we evaluate the condition again and check if we have to jump, and if we don't jump we return. And for this we have the convenience function gen loop to jump to something where we already know that we have to jump there. We already have generated the label. We don't need to use begin and end jump. We can just use gen jump, and we just go to begin, not B9, begin loop, and then we should be done. So the BC generator has an interpreter integrated that interprets the first function we have given. So it will interpret this function. The interpret function has the signature BC value as a result interpret. And then the arguments, which is just an array of BC values. And this makes it possible that every function we generate, regardless what parameter type it has, they all have the same signature, and it just works really nicely. Okay. So let's write lin the result. This M31 function converts an integer into the equivalent BC value, which is typed as integer. So we say write lin gen, because we aren't in the with block anymore, we have to call the gen out, interpret, then the array, and we want a BC value, immutable BC value 2 in fact, and we want to print the second power of 4, which should be 4 times 4. Which should be 4 times 4. So we should see 16. 4 times 4 is 16. Yes, right. Okay. Now we have to build it, and I forgot to start comments here. Okay. Now we built it, and we see BC cannot be read, so we give it BC, and we give it bc.com, and because we import those, apparently I made a typo here, yes. So it compiles, and I made another typo. It's not BCgen, it's BCgen with a capital G. Now let's mul loop label. Alright, there's an L too much. No. And result also has an LL. In there should just be one L. And now we run main, and we get 0. I suspect that we never set the result to 1. See that? We said that we have set the result to 1, but we just said gen temporary, and the temporary will be 0 by default, and if we always multiply 0 by something else, then we will get out 0. So we have to set the result to 1, and the corresponding call looks like this: PC value LHS, PC value RHS, and this is LHS equal to RHS, right? This is how set looks like. So we just do that. We wanted to set result to 1, right? So we just do it, set result, and we can't just set it to 1, because 1 is not a BC value. If we try to compile it, we get the problem that there is no function set. Okay. This is not a big deal. We can simply say we want an IMM32 with the value of 1. And IMM32, which we used here already, will just convert an integer number to a BC value that is that integer. Okay, and now we run it, and we get 16. And what should we get? 16. Okay. Now let's raise 4 to the 4th power, and I don't know what we should get because I'm not good at math, so let's just say 4 times 4 times 4 times 4 is 265. So what we should get now is 265. Let's I forgot that this doesn't have a make file. I just have to make it like this. Let's make main, let's press enter, and the value we get is 265, which is the value we should get. So I'm going to load this video up to YouTube, and if you have any questions regarding how this works, please let me know. in the comments or something. Okay. Yeah. Now I have to stop the recording and load this up. Bye. See you later.